Hi guys, welcome back to Calculus. So I have decided to dub this session Calculus After Dark. My sleeping schedule is so messed up that I am doing things like this in the middle of the night. Hopefully my sleeping schedule will get back on track pretty soon. But because right now it doesn't even really feel like there's enough coffee on planet Earth to get me back to where I was before. So welcome to the very first episode of Calculus After Dark. Now, tonight we're not going to be going over any of our most recent concepts from class. No infinite series, no sequences, nothing like that. We're just going to be working on a problem that I had a request about from one of my students. And I thought it was a really interesting problem. One of those types of problems where you have to be really strategic about exactly what to do, how to tackle this integral. We have a lot of tools at our disposal. And in situations like these, it may not be extremely clear what to do. So let's do a quick recap of all of the tools we learned in this class so far, all the nifty integration tools we've had to tackle a wide variety of different integrals. So the most basic one, I think, would just be U substitution. I mean, aside from just the normal stuff, like, for example, the integral of x squared turned into 1/3 x cubed. I mean, stuff that's not like that. Things that need a bit more effort and a bit more planning in order to properly execute. So I would say that kind of the bread and butter of a mathematician's arsenal, I don't know where I was going with that analogy, but kind of the bread and butter would be the concept of U substitution. We know it works really well in a wide variety of situations, and it even works really well in situations where you think it just wouldn't work well at all. So let's see if U substitution would be useful here. So typically the convention is to identify some kind of an inner function. So we can see we have a radical, we have something inside that radical. So we may be tempted to just say, hey, okay, looks good, this will be our u. So then du would have to be the derivative of whatever happens to be inside. And the problem with that is we don't have the derivative of u present anywhere in the integral, which makes things a bit complicated. So it would be really, really nice if this were an x to the 4th power, because then we would be in perfect shape just to do a quick substitution and be done in 30 seconds. But it can't be that easy, unfortunately. So believe it or not, we actually still can use U substitution. Not in the conventional way, not in the explicit way that we're used to doing it. We can use it kind of in an implicit way, and I'll show you exactly what I mean right now. So what I want to do is I still want U to be the function that's under the radical. I'm going to have that be our very first definition of the function U. We have U is equal to everything under the radical. So that would be U is equal to x squared plus 5. And I apologize for my handwriting being even worse than usual. I'm in travel mode right now. I don't really have access to the drawing tablet I'm used to using. So just a fair warning, my drawings and my writing won't be any better. In fact, they'll probably be a lot worse than usual. Just fair warning. So we're so programmed that whenever we see this, a u equals blah, 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 we are programmed just to instantly find du. That's just kind of our knee-jerk reaction. And it's right. That's exactly what we want to do here. Take the derivative of u with respect to x. And then what I want to do is I want to move the dx differential to the other side. So I'm going to multiply both sides by dx, but I'm also going to divide both sides by 2. Whoops. Multiply by 1/2 is the same thing as divide by 2. That looks nothing like a 2. So we have dx being multiplied on the left side and on the right side. Left side cancels out. So what we're left with is just 1/2 du on the left, which is equal to x times dx. Let's see if we have anything that can help us. So if this were just an x without a power, life would be so much easier. But sometimes life doesn't want to give us something too easy to work on. What's the point of going to school if you don't want to try new things and grow and learn as a person? I mean, I'm sorry for going off on a tangent, but I feel like this is important to say that you have to work out your brain in the same way that you would work out your muscles at the gym. By doing hard things, by doing really hard, painful, tedious things you'd rather not do. But the ending result is so, so great that it makes it all worth it. So doing really complicated problems and even playing a musical instrument is the brain equivalent to a workout. By doing hard things, your brain becomes better and stronger. So it's a really good idea to keep your mind sharp by doing integrals like this, exploring all the methods, and then even if it takes a really long time, keep working at it. And then eventually you'll have more neurological connections in your mind than you had before. You're a little bit smarter from having solved such a complex problem. All right, I think that's enough of my tangent for now. No pun intended. This is a math class. I'm funny. So we have our u under the radical. And like I said before I interrupted myself with that story, it'd be easier if that were a 1. But unfortunately, that's a third power. We can't just arbitrarily make that a 1. So what we want to do is we want to change the appearance of this integral. We want to change the appearance without changing the value. We want to make it look a little bit different without altering the value. So for example, something along the lines of multiplying by something over something. Something like that, we know that does not change the value. But actually what I want to do here is I want to rewrite this x cubed in a certain way so that we're able to utilize this definition of 1/2 du being x dx. So let's see what that looks like. So I'm going to make this x cubed. I'm going to turn that into an x squared times x. It's only algebra from the beginning up until now. No actual calculus is coming into play. At the moment, we're just doing a little bit of algebra, grinding through some algebra busy work to get this into a form that we do know how to integrate. So what was the point of what I just did? Why is it important to break up the x cubed into an x squared and an x? I am so glad you asked. So we want to go ahead and have this be part of our definition for 1/2 du. So if we remind ourselves what we wrote for 1/2 du, we wrote x dx is equal to 1/2 du. So our goal is just to replace x dx with 1/2 du. So I found the x and I found the dx. So x times dx is equivalent to 1/2 du. So what I'm going to do is I'm going to eliminate the x, eliminate the dx. I'm going to replace both of those collectively with this 1/2 times du. So we're going to have the integral going. I don't know where I was going with that. It's not going from anything. It's just an indefinite integral, not a definite one. So this is going to be x squared. And then, like I said, I'm going to replace this x and this dx with this 1/2 times du. They're both going to go away. We are replacing them with 1/2 du. So we have radical. But actually, you know what? Let's just go ahead and put the function under the radical that we already assigned. We have u is equal to x squared plus 5. Go for it right under the radical. And then what comes after that would be the completion of this equation that I wrote off to the side here. We have the x accounted for. We have the dx accounted for. We're going to replace them both with 1/2 du. 1/2 there, du. And then let's go ahead and just move the 1/2 out to the front of the integral. 1/2 right there. Whoa. And then we have dx. Or sorry, du. Oh, and I forgot the x. How embarrassing. I'm deeply ashamed. No, I was right the first time. So with Calculus After Dark, you have no real idea of what you're bargaining for. I could be on top of my game, ready to tackle things like this. I might be a bit slower. So it's a gamble, and I apologize for that. Just doing what I can. So I interrupted myself again in the middle of something important. So we have x dx is equal to 1/2 du. So we have the 1/2, we have the du. But then what do we have left? We only have an x squared left over next to that radical. So now let's see if we can go ahead and do a substitution. I think we might be able to. We already have u. We already have du. But what the heck are we going to do with this x squared? It's just chilling there. We don't really have a direct way of dealing with that. So let's do a little bit of more algebra witchcraft here and see if we can find an expression and then set x squared equal to some expression involving u. Because ultimately we want things to be in terms of u because that's our new differential. That is our new variable of integration. Before it was x and now it is u. So let's take the u equals x squared plus 5. I'm just going to solve for x squared because that's what we have right there and then do a direct substitution. So if we subtract both sides of this equation by 5, we're going to get u minus 5 equals x squared. Perfect, very nice. And then we're going to go ahead and just replace this x squared with u minus 5. This whole thing, u minus 5, is equal to x squared. We're just replacing it with this. We're just giving this another name. Has the same value, it just has a different name. Has some kind of identity crisis and it needs to come up with a name and skip town. So this would have to be u minus 5. We're putting things in terms of u instead of in terms of x. Next, what we want to do is maybe write this next part in terms of u. So this is going to be the square root of u. Of course, we still have du. And things are looking a lot easier. Remember at the beginning, it did not look like we wanted to use u substitution at all just because of the strange conditions we're given here. We're given the fact that the degree of the thing under the radical is 1 less than the degree of the thing outside. And that's why at first glance, it looked like u substitution would be completely useless for us. But it has a lot of these hidden tricks that you don't typically learn in a first-year calculus class. Things like this happen to be super useful. They happen to be things that you're going to be using many, many times throughout your mathematical career, no matter what you want to major in. Any calculus class in college, if you go beyond Calc 1, you're going to want to be able to look for clues like this and then be able to integrate accordingly. So let's go ahead and replace u with u to the 1/2, as we know it's equal to. So this is going to just be u to the 1/2. And then the nice thing is now we can just distribute and make it 2 separate integrals. So the first integral, well, actually, you know what? I lied. Before we even split it up like that, let's distribute. So we're going to distribute this u minus 5. We're going to distribute the u to the 1/2 to both of our terms into parentheses. We have 1/2 times the integral of u to the first. If we distribute u to the first times u to the 1/2, we would get u to the 3/2. And then we're going to have minus 5 u to the 1/2 power. So far, so good. And now all we really need to do is to integrate from here. We have things in a really nice form, really easy to integrate. So let's dive right in. So to integrate u to the 3/2, we're going to use that power rule for integration that tells us whenever we have a situation like this, be it a function or just a single variable raised to a power, we're going to add 1 to that power. So we're going to have 3/2 turning into 5/2. And then multiplying by the reciprocal of 5/2, which is 2/5. In addition to the 1/2 we already have hanging out outside. And then we have, this is going to be, well, u to the 1/2 is going to turn into u to the 3/2. So we're going to have u to the 3/2, and then the 5 being there has no real effect on the outcome of the problem, at least at this particular step. Where we have u to the 3/2. We're going to do what we did in the last term. We're going to multiply by the reciprocal of this fractional exponent. So we're going to multiply by the reciprocal of 3/2, which happens to be 2/3. So really what we have in our second term is going to be 5 times 2/3. And I'm going to clear away some space. We're almost there. We don't need most of this stuff. So what I want to do is I want to distribute the 1/2, but then I also want to substitute u back into the equation after I put plus c. How could I forget plus c? And we're going to distribute the 1/2. So if we multiply 1/2 times our first element, or sorry, not the element, but the first term right here, 2's are going to cancel. We're going to have just 1/5 u to the 5/2. And we have x squared plus 5 to the 5/2. And then over here, our fraction is going to be 10 over 3. So this is going to be 1/2 times 10 over 3. We're going to distribute this 1/2 to this 10/3. 1/2 times 10/3. And yes, I do have to write it off to the side of the page. Mathnasium, or I meant to say calculus after dark is kind of unpredictable. I don't trust myself to make accurate calculations in my mind, so I do have to work this out on the side of the page. So we're going to have 10 over 6, which reduces to 5 over 3. So we're going to have minus 5 over 3. And then we're going to have u to the 3/2. So that would be x squared plus 5 to the 3/2 power. What was that? Sorry, guys. I thought I heard something. I live alone, and I just freaked out for a second thinking, who's in my house? But I think it's just my sleep-deprived state making me hallucinate. I don't know, hearing stuff that's not really there. So enough tangents. We have 5/3 times x squared plus 5. And then from there, we're just going to make this into a 5/2 power when we add 1 to this existing power. Yeah, and that is pretty much it. Thanks for coming. And I apologize if Calculus After Dark doesn't quite meet your standards, but I did the best I can. So see you guys in the next video.